The recording. Okay, so welcome back, everybody. The next speaker is Ramiz Reza from the Indian Institute of Technology, Jammu, and he will talk about analytic m-isometries and weighted Dirichlet type spaces. Please, Ramiz.
First of all, thank you. I would like to thank the organizer for providing me this opportunity to present my talk here. So today my talk is not directly related with this week's themes, the branches of next spaces, but it is indirectly related. So if time permits, I will mention about this relation at the end. So today I will talk about these m-isometries and weighted digitized spaces. So before I introduce this m-isometry, let us see the simplest case, this weighted Riskless spaces. So which was introduced by Richter in 1991. So it is the Dirichlet space. So this consists, this is just the Dirichlet space, but with a weighted Dirichlet integral. So where the weight function is a positive harmonic function. So if you start with a measure mu on the unit circle, so mu is a finite positive Borel measure on the unit circle, and you consider this Poisson integral of the measure p mu z is a positive harmonic function on the unit disk. So in fact, every positive harmonic function on the unit disk can be represented in such a way. Then you consider this weighted Dirichlet integral, this t mu f. This is the weighted Dirichlet integral. So the weight function is the harmonic function p mu z, and you consider the functions, all such holomorphic functions on unit disk for which this weighted Dirichlet integral are finite. So Richter studied these spaces. So what I will do, I'll try to mention his result the way we have understood, and so that then it will allow us to extend, how we extend those results in m-isometry cases. So the simplest, let us see the simplest one. The simplest one, when the mu is the Lebesgue measure, in that case, you have this weighted Dirichlet integral is just a classical Dirichlet integral. And so if mu is the sigma, this d sigma, if you can easily compute, it will be just summation n mod a n square. Yeah. And where the function f is the summation a n j to the power n. So in this case, it is easy to see this. The classical Dirichlet spaces is actually subset of Hardy spaces. And now this Dirichlet integral is not a norm, it's a semi-norm. So if you add the Hardy norm, then it turns out to be a norm. And with respect to this norm, this classical Dirichlet space is a Hilbert space in which the monomials are orthogonal, and the norm of the monomial's norm square is n plus 1, which is linear in n. So once you have this monomials are orthogonal, there are very nice things happen. One such thing is the operator m is a unilateral weighted shift. And if you see the second order difference, since the monomial's norm square are linear in n, the first order will be constant and second order difference will be 0. Consequently, what you will get is norm of z square f. Because of the orthogonality, it will follow that this relation holds, norm of z square f square minus 2 norm z f square plus norm f square is 0. So when this holds for every function f in the classical Dirichlet space. So this is the same as saying that the operator mz is a 2 isometry. That means the operator mz, the multiplication operator by the coordinate function z, satisfies this operator equation. And in the classical Dirichlet polynomial are dense, polynomials are dense. It is easy to see because if the monomials are orthoforms orthogonal base. But all these results turns out to be very difficult to show when you are working with let's say the measure is not Lebesgue measure or not a scalar time of Lebesgue measure. If it is a scalar time Lebesgue measure, then almost all results hold true. But if the measure is not Lebesgue measure, then it is difficult to show all these above mentioned results. So for example, The first question is, I mean, whether, so if you start with an arbitrary measure mu, whether this the space d mu, the weighted Dirichlet space, whether it sits inside Hardy space or not. So the main problem is there is a weight function in the integral that makes the main problem. But you can compare this weight function. I mean, there are certain estimate of the Poisson integral. Using that estimate, you can get the estimate of the harmonic function p mu z. So it will be bigger equal to. So there is some comparison you can get in terms of. So left hand side function is a radial function. So now you can compute the integral, because now it is dominate this radial function. That integration is easy to compute. So you can compute this when the weight function is just a radial function. Then you can then you can compare the norm. So using that, the picture shows that in fact your Dirichlet space, the weighted Dirichlet space d mu subset of Hardy space, and consequently, with respect to the norm mentioned here, the d mu turns out to be a Hilbert space, and it is a reproducible Hilbert space. That means the evolution functions are bounded. One can also compute the norm, I mean, the semi-norm for a polynomial. With little bit of computation, it would turn out like something like this expression, which involves the coefficient of the polynomial and the moment of the measure mu. But for general function f, I mean, then there is no such good formula to evaluate this semi-norm. So what you can do at best is you can take the limit r tends to 1, and you can take over the r radius disk. Over the r radius disk, the function now behaves very well, and so then you can, so at best you can say it is a limit of some nice expression. So also, I mean, showing the boundedness of the coordinate function on this weighted Dirichlet space is not very easy. I mean, by an application of closed graph theorem, it is enough to show that if f in d mu, the multiplication by zf is also in d mu, then it follows that mz will be bounded. So to show this zf in d mu, it is you have to show this derivative, zf derivative, whether it belongs to the weighted L2 integral or not. So if you can easily check that, it means that we need to check that as zf prime is z of z time f prime plus f by product rule. So f prime is already in L2 of the weighted this weighted L2 space. So all you need to check whether for f in d mu, whether the f itself belongs to this weighted L2 space or not. So here we are demanding that whether some kind of embedding of the spaces are present or not. So what we need to show whether d mu is subset of, I mean, whether there is an embedding between the d mu and this L2 space. So in fact, I mean, there is a result that we already have shown that d mu is subset of Hardy space, and in fact, Hardy space sits continuously into this weighted harmonically weighted L2 space. So it turns, I mean, it was known that this p mu z dz is a correlation measure for the Hardy space, and consequently one gets that d mu actually sits inside this weighted L2 space, where the weight function is the harmonic function, positive harmonic function, and one gets that whenever f in d mu, z f in d mu, and then mz turns out to be bounded. There is another, I mean, nice formula about this d mu is, so if we already saw the formula for how to compute the norm of a polynomial. So if you see the difference of the zp and p, this semi-norm, this difference turns out to be integral over mod p square over the circle. So I mean, this kind of difference formula is very nice, because if you do second order difference, automatically you can easily check that the second order difference actually vanishes for any polynomial. And with little bit of limiting argument, one can also show that for any function f in d mu, this second order difference is 0, and consequently it turns out mg multiplication by z on d mu is 2 isometry. And then the question of polynomial density. I mean, there is a result by Richter. He shows that if T is not only 2 isometry, if it is even T is concave operator, that means T satisfies this operator equation. And if T is analytic, that means this hyperrange is 0, then T has wandering such property. That means T is generated by a kernel of T star. So from that, it actually one can, I mean, using this result, one can easily show that in this d mu space, polynomial are dense, because here a kernel of mz star is just constant, and by applying this result, we can easily see the polynomial are dense. This is one way to see the density of polynomial. There are many other ways. I will come to that in a moment. So I mean, Richter described the model for any 2 isometry. I mean, but if you start with any 2 isometry T, it turns out that the 2 isometry are decomposed in 2 parts. In one part, on the hyperrange, T acts as an unitary U, and in the ortho complement of the hyperrange, it acts as an analytic 2 isometry. And now the question is, what are all analytic 2 isometry? And that actually, I mean, when the dimension is dimension of kernel of A star is 1, then the model theorem of Richter says that the operator must be unitarily equivalent to mz on some d mu. For a unique, the mu must be the unique, the unique measure mu. So, and if the dimension is more than 1, then this measure will be replaced by some operator valued measure. And that has been done by Olofsson. So I will not go into that direction. I will, in this talk, I will stick to the case of when dimension is dimension of this co-kernel is 1. So the way we have understood the proof, that what you do is you take an element in the kernel of a star of unit norm, and you consider this matrix AMN given by this difference of the Gramian, a first order Gramian. I mean, first order difference of the Gramian. So in other words, this AMN is just a beta 1s acting on this SME inner product with SNE. And this beta 1s, which is the S star S minus I, it has some nice property. This S star beta 1s times S is beta 1s. That means this beta 1s S is S Toeplitz. Consequently, it follows that this matrix AMN is a Toeplitz matrix, and it is a formally positive definite. And from that, I mean, there is a famous theorem of Fraser-Riesz theorem, which says that when you have a infinite Toeplitz and formally positive definite matrix, it will be induced by a measure. So from that you get the measure mu. So it turns out this, and once you have the measure mu, then the rest is very. You can consider this d mu space, and you can check this using this difference formula. The first order difference of the Gramian is matches with this first order Gramian of the S. And consequently, I mean, the Gramian matches, and then the rest is actually bookkeeping. And so you just take the map. When the Gramian map matches, you can just say this: sending the map z to the power m to s to the power me is a isometry, and to show it is a unitary, and you need the wandering problem that this SME, they actually span the full Hilbert space. The linear span is dense. So using that, you can show that U is a unitary. That is the basic idea of the proof. I mean, using this idea, which extended our result actually. So before I come to our result, let us just recall the definition of m-isometry. And operator T is said to be an m-isometry if the mth order difference of T is 0. So for example, beta 1, the isometry is this first order beta 1 T is 0, but 2 isometry is beta 2 T is 0, and so on. And very recently, Reza actually described this cyclic. I mean, he found a model of all cyclic m-isometry using this higher order Dirichlet integral. So this higher order Dirichlet integral is, let's say, this nth order Dirichlet integral is given by this integral where the you see the nth derivative of f and its modular square, but the weight function is now this positive harmonic function p mu z times 1 minus mod z square for n minus 1. So now one can similarly consider the space H mu n, where you consider all function on the unit disk for which this nth order Dirichlet integral is finite. So it turns out to be a linear space, and it also turns out to be a subset of Hardy space like before. The case n equal to 1 is the Dirichlet, I mean this weighted Dirichlet space introduced by Richter. So like as before, I mean it turns out H mu n is also a Hilbert space, a reproduction of Hilbert space with respect to the norm given below. And again, I mean, you can compute the semi-norm on a polynomial for a polynomial, but for general functions, the computation will be very difficult. At best, you can say it's a limit of some nice expression. So that makes it hard for arbitrary mu how to deal with this. But like the, I mean, again, you by using this estimate of p mu z, I mean, using some estimate of the Poisson kernel, you can get an estimate of the harmonic function in terms of a radial function. Using that estimate, you can again show that multiplication by z will be, I mean, you can compare the norm and you can show that multiplication by z is bounded. And similarly, we found a, I mean, like in there's a nice difference formula we found that, I mean, this formula is actually known for polynomial. I mean, it was given in the Vidas paper. So we just extended it to for arbitrary function f, for which the nth order Dirichlet integral is finite. So what it happens if you compute the ZF nth order Dirichlet integral norm minus nth order integral Dirichlet integral of this f norm, then I mean the order actually decreased by 1. So it is d mu n minus 1f. So there are nice consequences of this. So if you take 2 order difference, then it decreases 2 order. And consequently, if you do n plus 1 order, then it vanishes actually. So it turns out that multiplication by z on this space are analytic n plus 1 isometry. And also, I mean, we have a formula like, so the difference, there's a dual formula, like from, if we do the difference, we get down to 1 step below, but we can also come up 1 stage above, like this, using this L operator. L is a backward shift operator, standard backward shift operator. And if you compute the iteration of L on the function f, and you compute the nth order Dirichlet integral, weighted Dirichlet integral, and you sum up, then what you get is n plus 1 order Dirichlet integral. So this, I mean, helps us in many ways. So you will see, I mean, in a moment. So there is another problem of approximation of functions through R dilation. So one question is whether given f in H mu, whether f are approximate to f or not. So the case of so to solve this problem, the standard approach is to find a constant c so that d mu n fr is bounded by some constant time d mu n f. So once you find such c, then it is actually easy to show that this approximation actually holds. So in case of n equal to 1, this weighted Dirichlet integral, it was, I mean, people have studied it very well, and the constant c equal to 4 initially found by Richter and Sandberg, and then Aleman found by the constant 5 by 2, and finally Shahasan improved the constant c equal to 1 using Dibban's-Robner space technique. But there are also other constant. If you want to, so let's say c, if you want c depends on r also, then you can get a much better constant, and this kind of approximation where c depends on the r, you can find in the work of Masregi and Ransford. So we also, I mean, find that for not only this holds for first order, but nth order integral also. The d mu n fr is also less equal to d mu n f, and consequently this FR approximate F as R tends to 1. And this actually, I mean, follows from induction. So the base case was the main thing. So what you need is, I mean, once you know the base case, using this summation formula, as I mentioned, this the dual of the difference formula, and using induction, one can show that this holds. And for the base case, I mean, as a consequence, one gets this polynomial density also one gets, because you can approximate F by FR, and FR are very nice function. They are holomorphic in a neighborhood of unit closed disk. So this FR you can approximate using the Taylor polynomial, so that you get the polynomial density in these spaces. And we also found an alternative proof to show in the case of n equal to 1, so weighted disk integral, how to show this d mu FR less equal to d mu F. So it turns out that it is equivalent to as a positivity of some matrices. So if you consider this matrix A, whose KL entry is minimum of KL, and this K minus Lth moment of the measure mu, then it is a positive different matrix. A is a positive different matrix. Now it turns out that d mu 1 of PR, that weighted disk integral of PR less equal to d mu P, is equivalent to saying that this matrix is formally positive semi-definite. And this matrix is positive definite was known to Simorin. I mean, he in his work one can easily see. I mean, he had already found this matrix is positive semi-definite, and from that it follows this d mu 1 of PR is less equal to d mu 1 of P, which is a base case. I mean, and by a little bit of a limiting argument, I mean, then one can also show that d mu FR is also less equal to d mu. So using this H mu n, one can construct many examples of analytic m-isometry. One can take a, let's say, tuple of measure, mu1, mu2, mu minus 1, this m minus 1 tuple of measure. So, and then you consider this this norm. First you consider the space H mu given by the intersection of H mu j of j, and you introduce the norm given in this way. So first you take the Hardy norm, then first order semi-norm of mu1, then second order semi-norm of the mu2, and so on. And it turns out that the multiplication operator on by the coordinate function on this space H mu is an analytic m-isometry with co-cardinal dimension is 1. Now, why it might be tempting to say that this might be the all analytic m-isometry, like it happened in the case of n equal to 2, but this is not the case. I mean, there are certain restrictions. I mean, the operator has certain restriction. So, okay. So just consider, let's say, this one example. There are two tuple H lambda and mu. So there are two measure lambda and mu, and the norm is given by Hardy norm, and the first order norm of lambda and second order norm of mu. Then one can easily, using the difference formula, we can check that beta 1 mz f naught plot f will be this quantity, sum of, and beta 2 will be this quantity. Now again, if we use this our summation formula, this using, we can show that this beta 1 minus this L star to the power beta 2 ln, that turns out to be positive. So that is a one restriction. I mean, so this is in these spaces always you have some extra positivity condition. So that so in general, if you consider m tuple of measure, then you find that this beta RT will be always bigger equal to this L star to the power n beta r plus 1 t of ln. L is this left inverse of the t, the Moore-Penrose inverse. So this is an extra condition. So, and we find this is our model theorem that if you start with an analytic m-isometry, if co-cardinal dimension is 1, then and you satisfy this set of positivity condition, then and the upper then t must be equivalent to mz for some tuple of unique measure mu1, mu2, mu minus 1. So this in some sense extends the result of Richter. but not in complete sense because you have some extra positivity condition, and that's why we get positive measure here. So I will skip the proof. The idea is almost the similar the way we have understood. So again, we need to construct some positive operator which are T to F these. So it turns out this operator A, beta minus, which we are demanding to be positive. This A turns out to be T to F these, so that we have a to F matrix which is formally positive, and we get a measure. And that is the once you get hold of measure, the rest is actually a bookkeeping. And at the end, you need a wandering success property because ultimately you have the Gramian will match, but so to show that you from that you will get U is an isometry, but to show U is a unitary, you need to show that this linear span of T to the power j is dense. That means you need this wandering success property. So that is the main ingredient, which we have shown that for any m-isometry, if we satisfy this set of inequality, then T actually has wandering success property. In fact, this is true not only in the case of m-isometry, it is also true for in the case of m-concave operator. And okay, with this, I just want to mention that all these spaces in these spaces I described here, the multiplication operator is expansive and it's analytic. So this space also can be realized as a Dirichlet spaces of HB, where B is not a scalar valued function. That B you have to think as a operator in Riskless function. So I mean, it will be very interesting to find which measure has connection. I mean, which measure will give rise which B. So that still we don't know yet the complete answer. So with this, I would like to stop.
Thank you. Is there any question? So I have a question again. The first one is, what is your H mu with a row in your second theorem?
Can you repeat your question?
In your second theorem, you have a space H mu with an arrow. What is this space?
So these are spaces for which, so this consists of functions which are holomorphic on unit disk, for which this you mean when you take the measure is sigma, I mean Lebesgue measure. I mean, is your question if the measure is Lebesgue measure, then what is the space H mu n?
No. How do you define the space H
Okay,
mu?
let me share the screen. Yeah.
Yeah.
Yeah, this is my H mu n is all holomorphic function f for which this nth order Dirichlet integral is finite. So if you take mu to be Lebesgue measure, then it turns out to be then the norm. You can easily compute the norm for if mu is Lebesgue measure. Then in that case it turns out to be k choose n. And just the d mu n of p will be.
I think
let's say if you want to compute the monomial z to the power k, its semi-norm, it will be k choose n. So monomial will be orthogonal in that case, and it will be k choose n.
Okay, but it was not that space. I'll talk about the space in your second theorem.
I think he's asking what is H mu bar? What is H mu over bar? That notation.
Yeah.
where h mu bar?
In
That
theorem
tuple, when
8.
mu is the tuple, what is that?
Oh,
What
okay.
is that?
Oh, that is tuple. Okay, that is intersection of h mu j. I mean, so you have n minus one tuple of measure, and for let's say mu1, mu2, mu m minus one. So for to consider function for which this jth order integral corresponding to the measure mu j has to be finite. So this is the intersection of all the function h mu j of j. So you see the jth order integral. So for mu1, the first order integral is finite. For mu2, the second order integral is finite. So that this norm is makes sense. The norm f square norm is makes sense. So it consists of all such function f for which all of these are finite.
Okay, thank you. I see now. I see the expression. Thank you. And all your spaces, your higher order Dirichlet spaces are embedded in each other. Yeah, or not?
Yes, yeah. There is a relation between using this difference formula. One can show that h mu n is always subset of h mu n minus one.
Okay.
So nth order will be always subset of n minus one order.
Okay, thank you. Maybe I have a last question. If I follow the talk of Pierre Olivier, the last talk, can you try to have the same kind of theorem like theorem 7 with another type of summation method?
Yeah, I mean, we haven't actually, I think there is some scope there, but we haven't explored that it yet. I mean, it is possible we can find some constant C which depends on R, which will be some better constant than one, but it depends on R. But we haven't explored it yet. I mean, I think the method used by this Java and Ransford will be helpful there. This Hadamard multiplier method. I think using that one can find some better constant.
So
we haven't explored that.
You are talking about the inequality here.
Yes. I mean,
yeah, but I talk about the summation method you used. So after the hand, you have the d mu n fr minus f, which tend to 0.
Yes.
So if I take another summation method instead of fr, I take
okay.
I don't know.
I think this Cesaro, we haven't actually completely solved it yet, but I feel that I have a feeling that using the Cesaro sum, actually one can show in this case Cesaro sum will actually converge. But I am not still sure, but I think that can be done using the Cesaro sum ability. One can show that not the Taylor sum, but the Cesaro sum will actually converge in this spaces.
Okay, thank you. So, is there any other question? So, if not, let's thank Ramiz again.